All right, now we're going to talk about regression analysis. Recall that in regression analysis, we're attempting to write the equation of a straight line that best describes the relationship between a dependent variable and one or more independent variables. If we only have one independent variable, that's simple linear regression. If we have more than one independent variable, that's multiple regression. In addition to being able to write the equation, we'd like to also have some idea about the strength of the relationship between the dependent variable and the independent variable or variables. And we'll talk more about that in just a minute. Let's look at a couple of examples first. In each of these examples, we only have one independent variable. The reason I want you to look at these, I just want you to get a feel for how you determine which is a dependent variable and which is the independent variable. So in the first example, we have a company that spends money each month on training its sales force and wants to know, does that affect sales? So of course in that case, the sales would be the dependent variable and the money spent on training each month would be the independent variable. In the second example, we want to know whether the size of a home has any impact on the heating cost. Well, in that case, then the heating cost would be the dependent variable and the size of the home in square feet would be the independent variable. The third example, we're looking at fuel efficiency, and we want to know whether the weight of a car affects the miles per gallon. So in that case, the miles per gallon is what we'd like to be able to predict, and that's the dependent variable, and the weight of the car is the independent variable. And the final example, we want to know whether the number of hours that students study for an exam have any impact on the exam score. So the exam score is a dependent variable. The number of hours studied for the exam would be the independent variable. Okay, let's first look at how we measure the strength of the relationship between the dependent variable and the independent variable or variables. That's done with something called the correlation coefficient. That value can range anywhere between -1 to 1, where -1 indicates a perfect negative relationship or inverse relationship. In other words, as one gets bigger, the other gets smaller. And a +1 indicates a perfect positive or direct relationship, where as one variable gets bigger, the other gets bigger. A value around 0 would indicate little or no correlation between the two variables, and values like 0.5, 0.6, or 0.7, or -0.5, 0.6, 0.7 are pretty good indicators of a reasonable relationship between the variables. Once we know what the strength of the relationship is between the two variables, we would like to know what's the equation look like that describes that relationship. So remember, this relationship must be linear. Both variables must be at least interval scale, which means that there is some meaning to the difference between the values, but there's no meaning to the ratio. For example, if I was talking about temperature, we know what it means. We know what the difference between 10 degrees Fahrenheit and 20 degrees Fahrenheit is. That difference makes sense, but it doesn't make sense to say that 20 degrees is twice as cold as 10 degrees. We're going to use something called least squares to determine the equation of the line, and we're going to let Excel do that for us. So here's a simple linear regression model where we only have one independent variable. That relationship between y, the dependent variable, and x, the independent variable, is given by y equals alpha, which is the intercept of the straight line, the y-intercept, plus beta, which is the slope of the straight line, times x. What we're going to use in regression is we're going to take some sample data, and we're going to use that sample data to obtain the equation y hat, where y hat is the estimate of y based on the sample data given a particular value of x, and that's equal to a which is the estimate for alpha based on the sample data, and B, which is the estimate for the slope of the line based on the sample data. So the regression equation will be y equals a plus b times x, where a and b are estimates for the intercept and the slope respectively. Okay, here we have an example of a situation where we have some sales representatives, the number of calls they made, and the number of copiers they sold. And what the company would like to know is, we expect there to be a relationship between the number of sales calls made and the number of copiers sold, but we don't know how strong that relationship is, and we don't know what that relationship looks like in the form of a linear equation. So that's what we'd like to determine. First thing we do is go to data analysis, go to correlation, highlight the data in columns B and C, including the labels, and we can see that the relationship is a pretty strong positive relationship, which would indicate that the more calls you make, the more copiers you sell. Okay, now when we look at the regression model, we're actually doing a hypothesis test. We're testing the hypothesis that beta is equal to 0. Now remember, beta was the slope of the straight line, and a value of 0 for beta would indicate that there's no relationship at all between x and y. The alternate relationship is that beta is not 0, and if we reach that conclusion, then we're saying that there is a significant relationship between the independent variable x and the dependent variable y based on whatever level of significance we choose. The test statistic will be either F or T, and they actually test the same thing when you're talking about simple linear regression. They are testing different things when we get into multiple regression. So I'll need to talk more about that as we get into the examples. A couple things that we look for in regression. The first is the coefficient of determination. That's the proportion or percentage of total variation in the dependent variable y that is explained or accounted for by the variation in the independent variable x. Well, what's that mean? What we mean by total variation is the difference in the y values and the average y value. That's what we mean by total variation. The R-square value ranges from 0 to 1, and because of that, it doesn't give us any idea at all about whether the relationship is positive or negative. Let's take a look at these two graphs right here to illustrate what we mean by R-squared. If you take a look at the graph on the left, you can see y bar. You see 4 values for y, and the difference between the values for y and y bar are the total variation. When we move over to the graph on the right, we can see that we have the regression equation, and now we still have the difference between y and y bar, but the percentage of that difference that's explained by the regression line is called the explained variation, and that's shown here in the brown, and the unexplained variation is shown in the blue. So we have the total variation, and that's divided up into explained and unexplained. Obviously, we'd like the unexplained variation to be small, which would make R-squared bigger. A second measure that we're interested in is the standard error of the estimate. Note that the formula for that takes the value for y and subtracts the estimated value from the regression line from that. So what you're really saying is that's a measure of the unexplained variation. We would like that to be small. We would like the unexplained variation to be small. In fact, if that's 0, that means the regression line perfectly fits the given data. The smaller this is, the smaller the standard error of the estimate is, the better the regression line is at estimating y given values for x. Okay, this is the regression output from the copier example that we looked at just a minute ago. You can see the multiple R, that's the coefficient, correlation coefficient. This is the R square value. Here's the standard error, the estimate. What we're really interested though in is the F test and the T test. Notice that in both cases the p-values are the same, and that's because in simple linear regression there's only one independent variable, and so what you're really testing for here is, in both cases actually, is whether or not b is equal to 0. Since the p-value is small, our conclusion is that b is not 0, so there is a significant relationship between the number of calls made and the number of copiers sold. This t-test down here tests the same thing. It tests a hypothesis that b is 0 because b is the coefficient for the number of calls made. So whether we use the f-test or the t-test in simple linear regression, we arrive at the same conclusion. The two values that you see here, these are the values that actually make up the regression equation. This is the A value, the estimate for alpha, the slope, or the intercept, I'm sorry. This is the value for the intercept. This is the value for the slope of the line, B. So our regression equation is copiers sold, Y, is equal to 18.947 plus 1.18 times the number of calls made. Here we have some possible values computed using the regression equation that we just looked at. Remember, the regression equation is 18.9476. This was the intercept. This is the slope. If you put 20 in here for x, you get 42.63. If you put 40 in here for x, you get 66.31, and so on. Okay, now I've switched over to Excel, and I've got the same copier data that we saw on the PowerPoint slides just a minute ago. And what I'm going to do is just walk through everything that we just talked about so you can see how we actually use Excel to get that information. So the first thing I'm going to do is go to Data, Data Analysis, and I'm going to find Correlation. Right here it is. I click OK, and I highlight the data here that I want to use to determine the correlation coefficient. I select the cell that I want to put the output, and we see that I get the same correlation coefficient that I saw in the PowerPoint slides earlier. No difference, and we didn't expect it to be different. Now I'd like to determine the equation of the regression line, so I'm going to again go to Data, go to Data Analysis, and this time I'm going to scroll down to Regression, choose Regression, and make sure that you get the right column in the right place over here under the input values. So the Y value would be the dependent variable, and that's the number of copiers sold. The number of sales calls made is the independent variable that goes here. We do have labels, and we want to put the output in cell E7. Oops. Here we have the values we saw just a minute ago in the PowerPoint slides. We see the f-test. We see the p-value for the hypothesis test that beta is equal to 0, and that can be done either with the f-test or with the t-test, but that's only true when you have simple linear regression. Note that the p-value for the intercept is not significant at the 5% level of significance. There's some debate as to whether or not you should include the intercept if it's not significant, but most agree that you should always include the intercept. Although, as I say, there's some debate about it, but I'm going to leave it in even though it's slightly insignificant. And what I'm going to do now is just show you how we can do the calculation that we saw with the estimates. Copiers sold, and that's an estimate based on the calls made. So let's suppose we make either 20 calls or 40 calls or 60 calls. How would we estimate the number of copiers sold? We're going to use the regression equation equals the intercept, and I'm going to make that an absolute reference, plus the slope, and that needs to be an absolute reference, multiplied by the number of calls made, and that needs to be a relative reference. So as you can see, we get the same values that we got. Oops. Didn't drag that down quite correctly. So you can see we got the same values that we got on the PowerPoint slides just a little bit earlier. So that's your example of simple linear regression. We're now going to move on to multiple regression. Okay, in multiple regression, note that we have more than one independent variable. So the regression equation now becomes y equals alpha plus beta 1 times x1 plus beta 2 times x2, etc. What we want to do is use the least squares criterion to estimate alpha with A, beta 1 with B1, beta 2 with B2, and so on. So we use the sample data to get an estimate for what our regression equation should look like. It also should be noted that if you want to just look at what B1 means, what that means is it's the change in y given a unit change in x, assuming that all other variables are held constant. Okay, so here we have a example where we have 20 different homes. We have sample data based on the heating cost of those homes, based on the average temperature outside, the number of inches of insulation in the attic, and the age of the furnace. What we'd like to know is, can we predict the heating costs based on the outside temperature, the attic insulation, the age of the furnace? We'd like to do that, but we'd also like to know what the strength of the relationship is between the dependent variable and the independent variables. So in this particular case, heating cost is the dependent variable. Mean outside temperature will be x1, the first independent variable. Attic insulation, x2, the second independent variable. And the age of the furnace is the third independent variable. If we run the correlation analysis on this data, we can see that the relationship between cost and temperature is an inverse relationship, which makes sense. What that tells us is as the temperature goes down, heating cost goes up. Also, the relationship between insulation and cost is inverse, which means the more insulation you have, the less your cost is. But the relationship between the age of the furnace and cost is a direct relationship, which tells us the older the furnace, the more the cost of heating. Okay, as we talked about in the simple regression model, we have an F-test and we have a T-test. The F-test is called the global test. And what you're testing in the global test is the hypothesis that all of the coefficients for the independent variables are equal to 0. In other words, none of the independent variables are significantly related to the dependent variable, and there is no way to predict the value for the dependent variable based on the independent variables. The alternate hypothesis is that not all of the coefficients are 0, which means at least one is not 0, or another way of saying that is that at least one of the independent variables is significantly related to the dependent variable. Now the problem here is we know that at least one is related, we just don't know which one. So we'll have to do further testing to determine that. And as I said before, the decision rule is the F test. That would be the global test, and we're going to take a look at that right now. So here we have a sample regression output for this particular data. If we take a look at it, we've got some things highlighted here. This F value is the F value for the global test. This is the p-value, which this p-value is 0.000006, a very small number. So what we know based on this value right here and the p-value is that at least one of the independent variables, temperature, insulation, or age, would be a significant predictor of cost. If we move on down, this would be the regression equation given the current independent variables being included in the regression equation. So the intercept would be 427. The coefficient for temperature is minus 4.5, which indicates an inverse relationship. Insulation is minus 14.8, which also indicates an inverse relationship, and we saw that when we looked at the correlation coefficients, and age would indicate a positive relationship. Now, we talked about the global test. We know that at least one of the independent variables is significant. How do we know which one? So what we're going to do now is use the t-test to test the hypothesis that each of the individual regression coefficients for the different independent variables is equal to 0 versus the alternate hypothesis that it's not 0. And so we use a t-test for that. If you look at the output that we had, these are the different t values and these are the p values that are associated with those tests. We can see from this that temperature is very significant. It's got a p-value of 0.00002. Insulation has a p-value of 0.006, but age has a p-value of 0.14. So what that tells me is that at the 5% level of significance, temperature is clearly significantly related to cost. Insulation is related to cost, but age is not a significant predictor of cost. Also, in this particular case, the intercept is highly significant too. So we would like to rewrite this equation and eliminate age because age is not a significant predictor of cost. So what we're going to do is rerun regression, and when we rerun regression, we'll take out age and see what the new equation looks like. By the way, just for your information, if there had been two of these independent variables that would have been insignificant, you would only take them out one at a time, and you would take the least significant out first, rerun regression, and then if it's still insignificant, you take the second one out. It's not likely, but it is possible that a independent variable can go from insignificant to significant when you remove another insignificant variable. Doesn't happen very often, but it is possible. Okay, so we run the new regression model without age. We see that, of course, here's the global test up here, and it's still significant, tells us at least one of the variables is significant. We already knew that. And now the intercept and the two remaining independent variables are significant. So we now have our final regression equation that the cost is equal to 490 plus minus 5.14988 times the temperature plus minus 14.718 times the number of inches of insulation in the attic. Okay, so now I'm back to Excel. I've got the same data we had just a minute ago, and all I'm going to do is run through what we just saw in the PowerPoint slide. So the first thing I'm going to do is go to Data, Data Analysis, Correlation, and just to show you that we get exactly the same data that we had before. And there we go. So this is the same data that we saw just a minute ago. That's how you do the correlation analysis. Now I want to go to Data, Data Analysis, and I want to slip down here and find Regression. Got to be a little more careful here. Note that it's got some values in there because I used this earlier, and so it's retained the other values, so you're going to have to overwrite those. No big deal, but in this particular case, the Y value or the dependent variable is cost. And the independent variables, now you got to be a little bit careful with this. The independent variables must be in contiguous cells. They must be together. You can't have space between them. We do have that in this situation. So I'm okay there. I do have labels. I'm going to put my output. I'll put my output right here. And you can see that this is exactly the same output we got a minute ago. And as we saw a minute ago, age needs to be deleted. I'm not going to go over all this again. We've already talked about it, but I do want to show you what we need to do to delete age. So we have to actually rerun our regression one more time. So now I'm going to go back to Data Analysis. I'm going to go to Regression. The dependent variable remains the same, but this time I do not want to include age in my independent variables. So I take age out. Now, by the way, if age was in the middle here, we'd actually have to delete it and put temperature and insulation together. The independent variables must be in contiguous columns. Okay, I want to locate my output. I'm going to go down and put it underneath the other output. So I'll just put it right down here. I now have my regression. And as we saw in the PowerPoint slides, this is my final regression equation. So I could actually calculate my cost based on temperature and insulation. So let's just look at a couple of examples. Let's look at a temperature of 35, insulation is 6 inches, temperature of 50, insulation 4 inches, temperature of 70, insulation 8 inches. And let's go see what the estimated cost would be. So we're going to have equals, the intercept must be absolute, plus the coefficient for temperature got to be absolute, multiplied by the temperature, which was in cell L46, plus the coefficient for insulation, and that must be absolute, multiplied by M46. And I get the estimated heating cost, and then I can drag this down for the other two cases. You might want to clean this up a little bit by going to format. You might want to format this as currency to 2 decimal places. just to make it look a little bit cleaner. But there we have our estimated cost. That concludes our discussion on multiple regression.